In this class, we shall discuss the classical limit of Schrödinger's wave equation. We start with the wave function written in this form. In the last class, we said that a complex function can be written in this form, right? Where rho here is actually psi star psi. Okay. Now we substitute this the wave function in this form into Schrödinger equation, the time-dependent wave equation, which was written as minus h bar square divided by 2m del square psi. Okay, of course there's functional dependence psi of x vector comma t plus v of x vector psi of x vector comma t is equal to I h bar partial derivative of psi with respect to time. Okay, we just substitute the wave function in this form into this equation. All right, and of course I'm not going to do the details of the calculation. These are just differentiations, so you can do that. All right, so substitute it in here, carry out, find these derivatives, and we'll get an equation. Now these are straightforward differentiations, and I leave the details of the calculation as an exercise for you. Right, in the end we get an equation of this form. Right, after all these differentiations, taking derivatives, using the product rules and all that, we get an equation like this. Right, so this is completely equivalent to the Schrodinger equation. It's just written in a different form. Now so far we haven't done anything special. We just wrote the Schrodinger equation in a slightly different form. Okay, let's now suppose that h bar can be regarded as a small quantity. Now immediately this does not make much sense, right? H bar has the dimensions of action, it's a constant, so it's not quite clear what it means to say that h bar can be regarded as a small quantity. Okay, so let's not worry about the precise physical meaning of this approximation yet, right? I think we'll be discussing this when we talk about the WKB, or the semi-classical approximation. All right, for now let's not worry about this. Let's just assume that a quantity h bar multiplied by modulus of del square s is much less than a modulus of del s itself, modulus square of del s itself, right? Modulus square of del vector s itself. All right, so for now our assumption just means that h bar multiplied by modulus of del square s is much less than modulus square of del vector s itself. All right, now let's collect the terms in this equation which do not involve h bar explicitly, which means that we are neglecting the small terms in some sense. All right, so I have written the equation 2 here again. This is the Schrodinger equation that we obtained by substituting the specific form of the wave function. All right, let's look for the terms that do not involve h bar. We see that the first term involves an h bar square, we don't take it. The second term involves an h bar, this is an h bar square divided by h bar, so that would be an h bar, we neglect that also. The third term, we see that there's an h bar square in the denominator, which will cancel with this h bar. Right, so there is a contribution from here. Let's write that down. There's a minus here and here, so this would become 1 divided by 2m. Okay, and we have got square root of rho from here. Okay, and modulus del vector s square, right, plus this term also involves an h bar. Okay, here there is a term that does not involve h bar, so that is square root of rho multiplied by v. And on the right side we have got the second term. Well, the second term on the right side will not involve an h bar, but there's an I here and an I, so that multiplies to minus 1. So this is minus square root of rho partial derivative of s with respect to t. So there's an equality and the minus sign. This is equal to minus square root of rho partial derivative of s with respect to t. All right, and there's a square root of rho on both sides, which can be cancelled. And finally, we are left with this equation: 1 by 2m modulus square of del vector s plus v is equal to minus partial derivative of s with respect to t. Or we can rearrange it to this form. All right, 1 by 2m modulus square of del vector s plus v of x vector plus partial derivative of s with respect to t is equal to 0. Okay. Now, if you remember your classical mechanics classes, you will see that this is the Hamilton-Jacobi equation. It was first written in 1836, and this s of x vector comma t is called the Hamilton's principal function. All right. So in the h bar tends to 0 limit, in other words, if you remove all the terms involving h bar, we see that classical mechanics is contained in Schrödinger's wave mechanics. So here we see that classical mechanics can be thought of as a certain limit of the Schrödinger's wave mechanics. Right? So we also have a semi-classical interpretation of the phase of the wave function. So this was the form of the wave function. Right? I have dropped the functional dependence, but it's there. Right? So here the phase of the wave function is s divided by h bar. Okay. So we see that h bar times the phase. Right? This is s divided by h bar. So h bar times this phase is equal to the Hamilton's principal function, provided that h bar can be regarded as a small quantity. Okay. Let us now look at a stationary state with time dependence e raised to minus iet by h bar. Right? We know that a stationary state has time dependence like this. For a stationary state, this means that if we have a wave function psi of x vector comma t corresponding to a stationary state, then we can write this as a part that depends on space alone, and then the time dependence is isolated as e raised to minus iet by h bar. Okay. Now we can write the wave function for a stationary state in this form. Right? When we write it in this form, this becomes, we'll have a function of space everywhere, right? Exponential. Instead of is by h bar, I'll have a function of space alone. So I'll write it as exponential I w by h bar, right? And then the time dependence is always of this form, e raised to minus I e t by h bar. This is for a stationary state. Okay. Now we can combine this and we see that this is equal to square root of rho of x vector prime and then exponential I. We see that this is equal to w minus et, w of x vector. I should write w of x vector here. That's a function of space alone. So we have got w of x vector minus et divided by h bar. Okay. Now, if you compare this with this form, we see that this corresponds to a separation of s as s equal to w of x minus et. Right. So this writing, looking at the wave function for a stationary state, this amounts to the identification of s as w of x minus et. In other words, we have separated the principal function into a space dependent part and a time dependent part. All right. Now you might be familiar again with these things from classical mechanics. Right. Here w of x was called the Hamilton's characteristic function, and you might have already seen that for a classical system with a constant Hamiltonian, the Hamilton's principal function can actually be separated in this form. Okay. All right. Now by looking at this form of the uh, principal function, right, we see that there is a wave associated with particle motion. Right? We can think of a wave associated with particle motion. Right? This is how it goes. We said that any function, right, of x vector is equal to constant defines a surface. Defines a surface. All right. So s of x vector comma t equal to a constant also defines a surface. Also defines a surface. Right. So we have something that defines a surface. Okay. So if we look at this, we can write if s has this form, right? If the principal function can be separated into a space dependent part and a time dependent part, then this equation s of x vector comma t equal to constant can be written as w of x vector minus et is equal to a constant. Okay. What does this mean? All right, we are looking at this surface, trying to understand this. This means that we can write this as w of x vector is equal to a constant plus et. All right. Now we see that for each value of time, this equation specifies a surface. Right? This equation describes a surface. All right. Let's say, for example, time equal to 1 second. Then we have a surface defined by w of x vector is equal to some constant plus e. This is a surface. All right. Now at time t equal to 2, we have a different surface. W of x vector now would be equal to a constant plus 2e. All right, because t equal to 2. Right? Now this is an equation for a different surface. So at time t equal to 2, we have a different surface. In other words, we have a surface that is moving. We have a surface that is advancing. Right? As time goes, this surface is advancing. So what we have seen here is that s of x vector comma t is equal to constant corresponds to a wavefront that advances in space, right? It corresponds to an advancing wavefront, as we have seen here. All right. Now this may become clearer if you look at the equation for the surface of a sphere. We know that the surface of a sphere is defined by x square plus y square plus z square is equal to some constant c square. All right. Now suppose, all right, this is of the form w of x vector is equal to constant. Now suppose there is also a time dependence which says that x square plus y square plus z square is equal to c square plus et. All right, say this is our w of x vector. All right. Now what does this correspond to? As time goes, we see that the radius increases. As time goes on, the radius increases. So this equation would correspond to a growing spherical surface that is actually growing up, right? Because we see that as time increases, this equation defines surface of greater and greater surface area, right? Or surface corresponding to higher and higher radii. Okay. Now I hope the idea is sufficiently clear. But what have we seen here? All right. What we have seen is that we know that Hamilton-Jacobi equation describes a particle motion. Hamilton-Jacobi equation is written. It describes a particle motion. All right. A particle with momentum, let's say del s divided by, del vector s. Okay. With momentum, p vector is equal to del vector s. All right. Remember, we are talking here classically. Right. We are talking about the classical limit. Okay, so we are looking at the equations in classical mechanics. All right. So Hamilton-Jacobi equation describes the motion of a particle. All right. But what do we see here from the analysis that we just had? We found that associated with this particle motion, we can think of moving wavefronts also. Right. So implicit in the theory is that associated with particle motion with p vector equal to delta vector s, which is the classical momentum, we have surfaces moving in a space. All right, it is implicit in the theory, right? And we can think of this surfaces as wavefronts, All right. Now we know that we are writing the equation, the evolution of the system in the configuration space. So these wavefronts are also in the configuration space. Generally, they are not. Generally, these wavefronts are not in the real three-dimensional space. It is, in general, a wave in the configuration space. Okay. For some cases, the configuration space may coincide with a real three-dimensional vector space. Right. But nevertheless, the idea is that we can associate some sort of wavefronts with particle motion. Right. So this is somewhere, this has been hidden in the Hamilton-Jacobi equation. All right. Now the momentum of the classical Hamilton-Jacobi theory is given by p vector classical is equal to del vector s, which is also equal to del vector w. Okay, this is consistent with the earlier identification of del vector s with some kind of velocity. Right. So let's come at this thing again. All right. So here, defining this p vector like this also defines the velocity. Right. So what we have here is that a velocity vector field. We have a velocity vector field. Right. So because first we find the Hamilton's characteristic function, and then the velocity is fixed by this equation. Right. Just divide this by m, and then we get the velocity. So this equation actually gives a velocity vector field, which means that at every point in space, if we are talking about a single particle, at every point in space, okay, this equation defines a velocity vector. Right. Now if we look at a particle trajectory, the velocity vector at each point, right, is tangent to the trajectory at that point, trajectory passing through that point. Right. So this, I think this is clear. Suppose we have some sort of a particle trajectory, and if you want the velocity vector at a point, all right, so the velocity vector at that point will be tangent to the trajectory at that point, trajectory passing through that point. So if you want the velocity vector at this point, you just find the tangent to that point. These are the velocity vector. In other words, if you have the velocity vector at every point, in space, then the trajectory is defined. Then the trajectory is also defined. In other words, this equation defines the particle trajectory. Okay, this is the equation that describes the particle trajectory. All right. So in classical mechanics, the velocity vector is tangential to the particle trajectory, and as a result, we can trace the trajectory by following continuously the direction of the velocity vector from here. All right. Now what we see here is that the particle trajectory is like a ray in geometric optics, because del vector S that traces the trajectory is normal to the wavefront defined by a constant S. Okay, so particle trajectory is defined by del vector S. All right. Now we can think of surfaces S is equal to constant. Surfaces like S of x vector comma t is equal to constant. Okay. Now we have already explained this in the previous class. If you have a function equal to constant, then del, the gradient of that function, is normal to this surface. All right. So if S equal to constant is a surface like this, all right, then del vector S is normal to that. Okay, so that's why we say here that the particle trajectory is like a ray in geometric optics, because the del vector S that traces the trajectory is normal to the wavefront defined by a constant S. So we have a wavefront associated with every particle trajectory, and the particle trajectory is moving. The particle trajectory, the momentum of the particle, is normal to the wavefront at each point. All right. Now clearly this is analogous with the case of ray optics and wave optics, or wave optics and geometric optics. In geometric optics, we have rays. All right. In wave optics, we have wavefronts. Right? We have wavefronts. Okay. So the same thing is described by wavefront as well as with by this geometric optics. All right. We know that the ray is in this direction, and then the wavefront can be described like that. Okay, so in this sense, we can say that geometrical optics is to wave optics. All right, the comparison between so just like the comparison between geometrical optics and wave optics, we can think of classical mechanics to wave mechanics, to Schrodinger's wave mechanics. All right, so it seems that just like the connection between geometric optics and wave optics, there seems to be a connection between classical mechanics and wave mechanics. Right now, this is implicit within classical mechanics itself. Right, we are just looking at classical mechanics, and we see that the Hamilton-Jacobi equation actually describes wave fronts associated with the particle motion. Okay. Now you might be wondering why this optical mechanical analogy was not fully exploited in the 19th century. Right? So why did people figure it out before? Okay, we said that in the Hamilton-Jacobi equation, even though we are describing particles, there are waves associated with S equal to constant, or Hamilton's principal function equal to constant. All right. So it seems that what we have seen is that this S equal to, or the Hamilton's principal function, let's put it like this, S in classical mechanics can be thought of as the phase of a traveling wave. So it seems that the waves, or the wave mechanics was waiting to be discovered within classical mechanics. All right, but people never thought of this because there was no motivation for this. There was no experimental motivation. There was no motivation for regarding Hamilton's principal function as the phase of some traveling wave. All right. There was no experimental result that suggested that maybe there are waves associated with particles. The wave nature of a material particle did not become apparent until the 1920s. Okay, so all this weird quantum mechanical behavior sometimes is associated with the wave nature. All right. So there is this old terminology about wave particle duality, etc. Right. Even though much of it we shouldn't take too literally. All right. As I said, these waves don't live in the real space; they live in configuration space, and these are waves of probability amplitudes. Okay, so which means that these probability amplitudes are given as complex numbers at each point. Okay, so we are not actually talking about any real wave in space. Right? We are just talking about probability amplitudes, complex amplitudes corresponding to every point in space, right? And in certain way, you can think of it as a wave, right? But you shouldn't take it too literally. Okay. Now, besides the basic unit of action h bar, right, which must enter into our equation for dimensional reasons, it was missing in the physics of the 19th century. Right? So there was no idea of this basic unit of action. Right. These are the reasons why, even though the mathematics was sufficiently developed to include waves into the particle equations, right? Equations associated with particles, people were not able to make use of this because primarily there was no motivation, and also people were unaware of this basic unit of action h bar, all right, a universal constant h bar, all right. So that was, I think we have discussed sufficiently the analogy between classical mechanics and quantum mechanics. We have also seen the classical limit of the Schrodinger's wave equation. Right? We see that in the classical limit, in some sense, when we remove all h bar, we get the Hamilton-Jacobi equation. And within Hamilton-Jacobi equation, we found that we can find these wavefronts associated with particle motion. Okay? With that, I'll conclude this session. Thank you.